Thanks a lot, Killian. Thanks to the organizers for inviting me here and giving me an opportunity to give this presentation. So it's really nice to be here. Um, so I'm going to talk about long-time behavior of certain infinite interacting particle systems. This is joint work with Shine Banerjee, and part of it is also joined with Peter Rudzes, but my expectation is that I won't get to that part, and that's why I put his name in parentheses. Um, these particle systems under a suitable reformulation, they can be viewed as reflected Brownian motions in infinite dimensions. So the picture to keep in mind is in this infinite orthant, a reflected Brownian motion. And analogous models in finite dimensions have been quite well studied, but in this talk, the focus is on the case of infinitely many particles. Let me first start the story with a case where there are finitely many particles. So um, And the description of the particle system is very simple. You have d+1 Brownian particles, so which means that you have d+1 particles which are evolving according to independent Brownian motions. And so with this little twist that the lowest particle or the leftmost particle gets a drift of +1 at any time instant. Um, so this feature of the dynamics introduces an interaction between these particles, right? Means after a while, the lowest particle who is getting the drift +1 may not be lowest anymore, and some other particle becomes the lowest particle, and now that gets a drift of +1. And so these kind of particle systems where the interaction sort of arises due to the relative location between various particles are sometimes also referred to as particle systems with topological interactions. So this is a phrase coined by Karinchi, Demasi, um, Prasuti in their recent book. This particular particle system is usually goes under the name of Atlas model after the famous Greek titan who supported the world on its shoulders. And so here the lowest particle should be thought of as Atlas. These models were first introduced in the context of stochastic portfolio theory by Fernholz and later. So I'm not going to write in detail the years various things happened, because if I do that, then I'll just keep writing names throughout the talk. And soon after that, there was a paper of Fernholz and Karatsas who studied this in quite some detail. And this simple model, turns out to have very rich structure, and this has been explored now in many different directions with many different points of views. For example, a large particle limit of the empirical measure of these particles and characterizing them through suitable McKean-Vlasov of equations or nonlinear Markov processes, proving propagation of chaos type results. For certain variations of these models, has been now well studied. These also arise in certain stochastic control problems that were introduced by David Aldous, and that has also attracted some attention. And then various kinds of limit theorems, for example, hydrodynamic limits and characterization through Stefan free boundary problems and fluctuation results with the space-time random fields described through stochastic PDEs. results of that type have been studied. And also scaling limits of discrete particle systems on lattices, for example, exclusion type processes, and characterizing the limits through these atlas type models have been explored. And discrete atlas models themselves are of interest in their own right. And recently, in fact, there are a couple of papers by Malesha, Menchikov, Popov, and Andrew Waite, who have looked at those models. So there's a rich literature on this, and they have been studied quite a bit. So let me describe this model a little bit in more precise way. So one can write down stochastic differential equations just describing the evolution of these d+1 particle systems in the following formal way. So let me call ui of t to be the state of the ith particle at time t. So I here is according to some initial labeling of the d+1 particles. Then formally, you can write down the evolution in the following manner. So you get a drift of +1 if this is the lowest particle. So UIP is the minimum of UJT. Otherwise, you just get a Brownian motion. So here WIs are just d+1 independent Brownian motions. And so you immediately realize that this is a slightly non-standard type of a stochastic differential equation in that the right-hand side is not a nice continuous function. And so well-posedness itself is a question to ask. And that result for these type of dynamics, were first considered by Bass and Pardue, who showed that there is weak existence and uniqueness of this system of equations. Yeah, where did DT go? Weak existence and unique. So that's, I think, 1987. Let me just make sure. Yeah, so that's 1987, I think. So they looked at weak existence and uniqueness. And later on, in a paper of Ichiba, Karatsas, and Shklonikov, it was shown that, in fact, here you have pathwise existence and uniqueness. So that requires more work. And I think that's like, yes. So that one, right. So I don't think this follows directly from Beretnikov's theorem. Okay, so I need to think about it. So yeah, so perhaps it also. Okay, okay. So yeah, maybe let's talk about it and see if this is good. And that is for weak existence uniqueness. Right. Yeah. So Beretnik uniform electricity. I think there is an extra. Okay, let's talk about it. I think I don't think it's directly covered by that. I see. I understand. So Yeah. So I guess the work of Ichiba, Krasas, and Shklonikov also allow for more general diffusion coefficient. So that result, I guess, did not follow from Veretnikov work, but perhaps this one is covered by Veretnikov. I think you're right. I think you're right. Okay. So right. Once you have strong existence and uniqueness, you can talk about the solution process, and you can rank the particles. So I'm going to denote by y1t, y2t, y d plus 1t, the states of the d plus 1 ranked particles. And it will be slightly more convenient to look at the gaps. And so I'm going to define ZIT as like that. And one advantage is that the state space here is a little bit simpler. Instead of looking at processes that live in this wild chamber, you look at essentially processes Z, which are now take values in the positive orthant, non-negative orthant. And these kinds of, and also, by an application of, for example, Tanaka's formula, one can check that if you write down the evolution for Z, that is given by a reflected Brownian motion in this non-negative orthant with a very specific type of reflections at the boundary. And these, kinds of reflected Brownian motions actually are very classical objects. They have been studied quite a lot in stochastic networks theory. So we have an expert in the room. They go back to, for example, the works of Riemann, Harrison, Williams, and so on. For example, in this particular setting where the lowest particle gets adrift, this introduces a certain stability in the dynamics of this gap processes. So these I refer to as the gap processes. So they introduce certain stability in these in this Markov processes living in the positive orthant. It follows from the work of Harrison and Williams that in fact, this Markov process is positive recurrent. Its unique invariant distribution takes a very simple product form. So I'll denote this by pi. And this is simply given as the product of exponentials in this manner. And this is the work of Harrison and Williams, in I think sometime in 1987. This was also rediscovered later by Hall and Pittman in the context of Atlas model, and that's 2008. And in later works, convergence to properties to these stationary distributions, starting from an arbitrary initial distribution, convergence to stationarity, and exponential rates of convergence, geometric ergodicity, in total variation norm, for example. They have been studied as well. And this was a paper with Chi-Hun Lee, and that's 2007. And then precise dimensional dependent rates for convergence to stationarity were in a paper with Banerjee. And a later paper that Chine wrote with Brendan Brown. So yeah, in the finite dimensional setting, the story is very complete, and you know ergodicity, you know rates of convergence, and so on. Yeah, so this Z is so this Z is a D-dimensional thing, and so this is the stationary distribution of this D-dimensional Markov process. That's right. So Z is Z1, Z2, ZD. Sorry, I can't write boldface in chalk. So, so yeah, so Z is this object. And this is actually maybe a side remark. So this is already an interesting result, right? That, there is a non-trivial dependence between the coordinates, the dynamics of these processes. But somehow at time t equals infinity, these coordinates disentangle and you get this product form stationary distribution. Okay, so as I said, the focus here, so I'd like to maybe keep this. So the focus here is in the case where D is infinity. So we are interested in the case where D is infinity. So again, description of the model is very simple. This time you have infinitely many particles, and they are evolving according to independent Brownian motions, except the fact that the lowest particle gets the drift +1. And formally, once again, one can write down stochastic differential equations for the evolution. So maybe I'll once again denote by UIT the state of the ith particle. So this is now I in N0. And it will be convenient to introduce YIT here as well, which is the state of the ith ranked particle. So Y0T is the leftmost particle, Y1T is the next one, and so on. And so formally, one can again write down the evolution in the following way. So this is Yi of T, like that. But here, immediately one runs into issues in that, when you have infinitely many particles, the lowest particle may not even make sense, right? It means you could have accumulation points, or the points may diverge to minus infinity. So in general, making sense of the lowest particle may not be possible. So these, technical things were resolved in a paper of Sarantsev, which is 2017, which actually built on this paper of Ichiba, Karasar, and Shtronikov that I mentioned earlier, and said that if the initial configurations are nice, that they're not too dense, for example, then you can make sense of things. And so the condition that it was introduced in this paper of Sarantsev was the following: that if you look at this, if this is finite for all alpha greater than 0, then it turns out, you can make sense of this equation. This equation has a unique weak solution, and the solution process at any future time also satisfies this condition. So, so for example, if I denote by B to be the collection of all X in R infinity, then the solution U lives in V. So there's a unique weak solution, and it takes values in V. And intuitively, the way to think about this condition is that the particles cannot be too dense. They can't be too tightly packed. So in particular, it says that below any level, there are finitely many particles. And another way to think about this condition is that if you look at the distance between the ith particle and the first particle, that grows slightly higher order than square root of log I. So something like that. So that's the spacing which is allowed under this condition. So yeah, so once again, once one has this well-posedness, one can talk about the solution process, and one can rank these particles because the solution lives in this space. So the rank particles states are well defined. So here, I didn't emphasize it in the finite dimensional setting that there's always an issue about ties. And so, for example, you break the ties in a lexicographic order, so that there is a unique way to rank them. And again, once one has the evolution of UI, one can also write down the evolution for YIs. And again, this is an exercise in Tanaka's formula. And what you see is that YIs, the evolution of YIs involves certain local time terms. So the dy of t, so it will be the lowest particle gets a drift. So indicator of I equals 0 dt plus dBit. And these are, again, independent Brownian motions, but different from the ones that appear in the equations for UI. But you can write BI in terms of WIs. And then there are local time terms. And I is 0, 1, 2, 3, so on. And L0 is just 0. And here Li is the intersection local time between the I minus 1th and ith particle. So I won't write it all. So Li is this intersection local time. So I just want to emphasize that I'm trying to stay away from the term collision local time, because it's not that these physical particles are actually colliding, but it's still a convenient kind of picture to keep in mind that these are the times where yi is equal to yi minus 1. So once more, it is easier to look at the gap processes. So I'm going to denote Zi as yi minus 1. So this time I is 1, 2, 3, so on. And now Z is this infinite vector, which is R plus infinity valued. And we are interested in behavior of this process, particularly long-time behavior of this process. And so the first result in this regard is a result by Paul and Pittman, who showed that this R plus infinity valued Markov process. So by the way, showing that this is a Markov process requires some work, means we looked in the literature for a while, we couldn't find it, and so we had to prove it for ourselves. But one can show this is a Markov process, and this Markov process has at least one very simple form stationary distribution. So that's Paul and Pittman, which is 2008. that the following infinite product um, of exponential 2's is a stationary distribution. And the fact that this emerges as a stationary distribution actually should not be too surprising. If you recall, for finite Atlas model, we had the following as a stationary distribution. And so if you just formally send d to infinity, you arrive at this distribution. And so one can show that this is indeed a stationary distribution of z. And actually, this paper also made an interesting conjecture that this is the only stationary distribution of this Markov process. And this was shown to be false. And so there was a paper of Sai and Sarantsev. And this was about 10 years later, who showed that there is actually a one-parameter family of product forms stationary distribution for this Markov process, which is given explicitly like this. And A can be any parameter greater than or equal to 0. So all of these are stationary distributions. So once again, this time Z is this infinite vector, Z1, Z2, like this, and it takes values. It's a stochastic process, so maybe I should put a T, and it takes values in R plus infinity. Right? Yeah. So this means that Z1 has exponential 2 distribution, Z2 has exponential 2 distribution. So it's an infinite product of yeah. Okay, so these were all shown to be stationary distributions, and there is actually a qualitative difference between this type of a stationary distribution and this one. So, for example, if you view this stationary distribution as describing the gaps of a point process, then in the first case, this is the point process is like homogeneous, like a Poisson process with ray 2, whereas in this case, the point process has density which is exponentially growing. So it's like density is like e to the power ax rather than being constant. And the density parameter depends on a. So the higher the value of a, the larger the exponent in this exponential density. So these particle profiles are extremely, extremely dense. So these look like very exotic kind of stationary distributions for this very simple Markov process. Questions? Huh? There might be others as well. And in fact, that's one of the big open questions here. Yes, so I'll come to that. Yes. So very good question, and I'm going to come to that as well. Okay. So, just as in the finite dimensional setting, where we were interested in convergence to, starting from arbitrary distributions, convergence to stationary profiles. One is interested in the same thing here, except now there is not a unique stationary distribution, and so global convergence questions don't make sense. And so the natural questions to ask are of local stability and maybe identifying domains of attractions of these various invariant measures. So that's one question we are interested in, domain of attraction of various invariant measures. So that will perhaps get towards question you were asking, how do you get to these kind of stationary distributions? And the question that Andrew was asking, whenever you have multiplicity of invariant measures, you want to characterize the ergodic structure of that Markov process. So one would like to say, what are all the extremal invariant measures of this Markov process? So questions of ergodicity and extremality. So that's the second question that I'd like to get to. And the third question, which unfortunately I would not be able to get to, is about fluctuations from stationary profiles. But that's also an interesting story there. So let me first get to talk about domain of attraction. So let's maybe start with a definition. So if nu is a probability measure on, remember the space V, which is the space of nice configurations. So for a nu like that, I will denote by nu hat t, the law at time t, when the law at time 0 is nu. So nu hat t is just the time t law when the Markov process is initiated at the measure nu. That's all. And nu t is the time averaged object. And so here is a terminology. We say nu is in the strong domain of attraction of phi a if this nu hat t converges, say, weakly to pi a as t goes to infinity. And it is in the weak domain of attraction if this time average law converges to pi a as t goes to infinity. And we like to say, describe the domains of attractions of various pi a's, either in the strong sense or in the weak sense, whatever our tools allow us to say. So, yes. Oh, what's that? Oh, weak convergence. Weak convergence of probability measures. Okay. So now, so these questions have also been studied. The first result on this was again by Sarantsev, which is 2017 again. And so what he showed was that if nu stochastically dominates pi 0, so the way to think about this is that pi 0 corresponds to these homogeneous gaps, Poisson 2-point process gaps, and nu corresponds to gaps being larger. So particles less densely packed than this homogeneous configuration. Then nu is in strong domain of attraction of pi 0. So maybe the picture is like this. Think of a spring with this homogeneous gaps. If you pull this spring, so the gaps are now a little bit bigger than the initial ones, then this spring relaxes to this distribution given by pi 0. Just a couple of years later, there was a very nice paper of Dembo, Jara, and Ola. And which, gave a much more general set of conditions for a measure to be in the domain of attraction of pi 0. So writing their conditions takes time and they're technical. So instead of writing them, I'm just give you just flavor of it, and later on I'll talk about examples and maybe say something more precise. So let nu be a probability measure on B, and Z0 be distributed as nu. So Z0 describes the gaps whose distribution is given by this measure nu. So so the three conditions introduced in this work, and I'm not going to write these conditions, but just tell you that the first two conditions say that the gaps are not too small. And so gaps are not too small. So that's analogous to what is assumed in Saransev. So it goes in a very similar spirit as Saransev's condition. But then there is a third condition which says that the gaps are not too big. And this is a bit unexpected and unintuitive, non-intuitive condition. In particular, with this condition, the results do not capture the whole range of scenarios that are captured by Saransev, because Saransev doesn't require any upper bound on how big the gaps can be. And then under these technical conditions, they show that mu is in strong domain of attraction of pi0. And one other remark I'll make about these conditions is, in the conditions that I've not written down, is that their conditions are violated if even one of the gaps are zero with positive probability. Condition does not hold if Zi of 0 is 0 for some I with positive probabilities. Which is again kind of unexpected, because one would expect that what happens to few initial gaps should not impact drastically the domain of attraction, the long time behavior of this infinite vector stochastic process. So these are a couple of things I want to keep in mind. And the final statement is that prior to our work, there was no result for A not equal to 0. And there's good reason why A not equal to 0 is harder to analyze. And if, for example, one looks at the techniques developed in Demboyar and Ola, their idea is to compare the infinite Atlas model with a finite Atlas model. So, finite Atlas model is a nice reversible Markov process. So you have tools of, relative entropy and Dirichlet forms that you can use to study rates of convergences. And so the kind of things they do is they show that if you look at the finite Atlas model, and if you let the number of particles d go to infinity and t go to infinity simultaneously in a suitable manner, then the first k gaps converge to the first k marginals of pi0. And then they also argue that, on any compact interval 0 to t, you can find a d which will depend on t. So the larger the t, the larger the value of d, says that this d-dimensional Atlas model is uniformly close to the infinite Atlas model over that compact interval. So some kind of a comparison between finite Atlas model and infinite Atlas model, which allows for some kind of coupling ideas. And but that's not going to work here, because if you remember, the finite Atlas model has a unique stationary distribution. Remember that stationary distribution 2, 1 minus I over d plus 1. And that stationary distribution converges to pi 0. So in some sense, this finite dimensional approximation idea is designed to select the special stationary distribution pi 0. And so if you want to find domains of attractions of these other exotic invariant measures, this finite dimensional approximation, at least the way formulated here, may not be directly useful. Now, there are ways to write down finite dimensional models whose stationary distributions converge to pi a rather than pi 0 by introducing certain perturbations. And these are also nice reversible Markov processes, so lots of tools are available. But there's a key step where you have to couple this finite dimensional model with the infinite Atlas model, which with these variations is hard to do. So at least we were not able to implement that strategy. And so we tried it quite a bit. And so we gave up on that idea, had to do something else. So, so here is the first result. 20 minutes, okay. So let me first talk about what to expect. So a terminology for two probability measures, mu1 and mu2 on spaces S1 and S2, we say x comma y is a coupling. This is a pair of random variables given on a common probability space of mu1 and mu2 if x is distributed as mu1 and y is distributed as mu2. So just a terminology that I'll use. And let's make the following observation. So suppose, so let Wi be IID exponential 2. And consider for a prime greater than 0, VAI, which is WI 2 over 2 plus IA, and V A prime I, which is 2 over 2 plus I, A prime WI. So by elementary scaling properties of exponentials, we see that if you look at this infinite vector, VAI, then this is exponential. This is precisely the distribution pi a, right? Exponential with the parameters 2 plus IA. And similarly, VA prime, this is pi a. And of course, pi a prime is not in the domain of attraction of pi a. It is in the domain of attraction of itself, pi a prime. And if you look at the L1 distance between these two coupled processes, so if you look at VAI minus VA prime I, then from these formulas, you can see that these L1 distance is like log D. So what this simple back of the envelope calculation suggests is that log D distance is already too much for one to be in the domain of attraction of the other. The log D distance is too much. And what our result says is that if it is slightly smaller than log D distance, then it is okay. So what do I mean by that? So here is a precise statement. So this is this appeared a couple of years ago. So fix a greater than 0. And suppose nu satisfies the following. There is a coupling and U VA. So U is distributed as nu and VA is distributed as pi A, such that the L1 distance, as I said in words here, grows slightly slower than log D. Namely, if you look at UI minus VAI, some I going from 1 to D, and you look at maybe log D, and you divide by log D, you look at lim sup. So yeah, so this is the first result which covers the case A greater than 0. And I'll write a second part which talks about A equals 0. But before that, maybe just one example to kind of get a sense of what this condition allows. So suppose, for example, nu is two plus IA plus lambda. So this nu can be thought of as a perturbation of pi A. Just write like that. By these parameters lambda I. And so the question is, one expects that if this lambda i's are sufficiently small, then this nu should be in the domain of attraction of pi A. Question is how small is allowed. Certainly lambda I, which are like, I A prime, that's not allowed, because then this nu will be in the domain of attraction of pi A plus A prime. But what our result says is that if lambda is of slightly lower order than this linear order, so for example, it says if lambda I is little o of I over log I, yeah, log I, then nu is in this, I didn't write the punchline. Then nu is in weak domain of attraction of pi. Any questions on this? Mutually singular. Yeah, mutually singular. Yeah. Oh, these two. These two are. Yeah, yeah, yeah. Right. This result just says that if there exists a coupling, and in these type of examples, you can construct the coupling very explicitly. Yeah. So that was the first part. They may be negative, but there's a condition on how negative it is. Yeah. Lambdas can be negative as well. Okay, so yeah, good point. our results give weak domain of attraction. In a second, I'm going to talk about the proof idea if I have a few minutes, and then it will maybe come back to your question that why we can only handle weak domain of attraction. Right now, there are no results of strong domain of attraction for pi a. Yeah. So the second part is for a equals 0. And there as well, we have some results. Suppose nu satisfies the following. There is a coupling U and V. So U is distributed as nu, and V is distributed as pi 0, such that if you look at I equals 1 to D, Ui min Vi 1 over square root of D. Then nu is in weak domain of attraction of pi 0. So couple of observations on this condition. So remarks. So first, if nu stochastically dominates pi 0, then you can find a coupling where Ui is greater than or equal to Vi for all I. And so this minimum just becomes a Vi. And then this is infinity just by the strong law of large numbers, right? Because 1 over D Vi will converge to a positive quantity. So this is smaller order. So this goes to infinity. So it satisfies the condition. So this in some sense recovers Sarantsev type result. But of course, we only show weak domain of attraction, whereas Sarantsev in this case shows strong domain of attraction result. The other thing to observe about this condition is that this is insensitive to what happens to first few coordinates because it involves a limit. So first few coordinates could be 0 if you wish. So for example, a condition which was recall not allowed in the paper of Dembojara and Ola. And the final thing to observe is that this condition doesn't require any upper bound, that the gaps cannot be too big, because of this infimum that appears here. So there's no requirement of that gaps cannot be too big. So once again, that's qualitatively different and in alignment with what Sarantsev's results say. So, but maybe I'll make one more comparison. So let's see how much time I have. So not too much time. So I'll make one more comparison with the work of Dembojara and Ola. And so the canonical example or a representative example they give for situations in which the condition is satisfied is the following. So so let nu be the law of U. And suppose Uj are of the form lambda j, theta j, where theta j are IID, non-negative, and satisfy the following conditions. Expected value of theta 1 is finite. Expected value of log of theta 1 minus is finite. So for example, this doesn't allow theta 1 to be 0 with positive probability. And suppose one of the following holds. Either these lambda j's are uniformly bounded above and below, away from 0. Or if they go to 0, then they don't go to 0 too fast. And if they go to infinity, they then don't go to infinity too fast. So let me say this precisely. Or theta j are exponential ones. And one of the following. Lambda i's increase to infinity, but not too fast. Lambda to the power beta, I to the power beta. So this sum is finite, so they can't grow too fast. Or they go to 0, but again, they can't go to 0 too fast. So 1 over square root of I log I sum j from 1 to I. Lambda j goes to infinity. If this holds, then nu is in strong domain of attraction of pi 0. So for this specific example, we can compare their condition and our condition. And what our condition requires is that instead of this, we require theta 1s are positive with positive probability. And instead of this, we require lim inf of lambda j is positive. So of course, if this is satisfied, then certainly this will be satisfied. And we do not need this condition. And for this part A, again, we don't need lambda I to go to infinity at certain rate. All we need is lim inf of lambda j is greater than 0. Again, if this condition is satisfied, certainly this condition is satisfied. And for this case, we don't need this part of the condition, but we need this condition. So, so it allows for example, non-monotonic type of behavior. And of course, what we show is not this. We show a weaker result. So we show a weak domain of attraction. So that's how our result kind of compares with their. Right. So I 1 minute. So I will just say that proving this requires, and I didn't get to the whole extremality business. Just kind of overestimated how fast I can write. And proofs are based on coupling ideas. So you have to you consider synchronous couplings of two ranked Atlas models starting from two different initial configuration, and you estimate the differences using estimates on excursions and arguing that after every excursion is completed, you get a certain amount of contraction. And so you have to control the number of excursions and sizes of excursions. And so going back to the weak domain of attraction, that's also the reason why we can only prove weak domain of attraction results because in studying these excursions, we have control on what happens when you're going to the outward part of the excursion, but not a control on what happens in the backward part of the excursion. And so overall, this only gives you control on time averaged quantities. And so we don't have a way to make statements on a strong domain of attraction types results. But these tools allow you to to talk about weak domain of attraction results. And extremality, okay, I'll just give you the punchline that, pi AD, so pi A, sorry, are all extremal. And but we don't know if these are the only extremal invariant measures. That's an open problem. So there is a related model called the Harris model, where they're just Brownian particles. So the lowest particle doesn't get any drift. And there's a full characterization of all extremal invariant measures. But for more general kind of things like Atlas model or more general situations than Atlas model, we can say that these are extremal, but we can't say that these are the only ones. But we can say the following. We can say that these are the only product form extremal invariant measures. In fact, these are the only product form measures, extremal or not. So that we can say. But I didn't get to that part of the story. Yeah, so I'll stop here. Yes, so extremal simply means invariant probability measure for a Markov process is said to be extremal if it cannot be written as a proper convex combination of two other distinct invariant probability measures. So in other words, if nu is an invariant measure and it can be written as theta nu1 plus 1 minus theta nu2, where these are also invariant measures, and theta is greater than 0, then you must have that nu1 is same as nu2. And so in the set of convex sets, these are extreme points of these convex sets.
Fiction, the directions,
so these are all invariant measures, for different A are related to the same reflection directions. So I would say that it doesn't change the reflection directions. But there is a point I think I can make, is that I made this remark that you could write down finite dimensional approximation, the finite dimensional models whose stationary distributions converge to pi A. The way, and they differ from the finite Atlas model. And the way they differ is not in any reflection mechanism, but in the form of the drift. So, so there is you add a certain drift to different coordinates, and that, converges to these more general stationary distributions, right? Yeah. Hello. Thank you.
That's from the d-dimensional case and the difficulty of that, but also the ingeniousness of ways of getting changing it. So I just wondered if you could say a word about that. I mean, I suppose one thing one thinks of is to put the topmost particle with a small drift in one or other direction.
That's exactly what you do. Yeah, so you kind of add a drift A to the topmost particle. There is also a way to distribute the drift in some way that you get to the same stationary distribution, but that's the simplest way to do it. You kind of put some slope on the topmost particle.
So as you said, homogeneous.
Yeah.
It's a big difference.
Yes, that's the problem, that you can't sort of couple it with the infinite Atlas model in a convenient way. At least we tried and we were not able to do that. Yeah. That's exactly. That's right. The leftmost particle. That's right. So the leftmost particle for theta 0 case, it's known that, it has these fractional Brownian motion fluctuations. It is, it will wiggle around, but if you divide by, t to the power 1/4, that will converge to a fractional Brownian motion. But if A is positive, it actually drifts. So what you can show is that the leftmost particle minus AT/2, that will, if you start from these stationary gaps, that it will converge to a limit which sort of looks like a gumball, but not quite gumball. Difference of two gumballs. Yeah, yeah. That's exactly what's going on. Yeah, the gap, independence of the gap certainly plays a role as well. See, since we are starting from stationarity, you can look at yeah. So this is a longer story. So yeah, you kind of look at a stationary point process. And you compare x1 of t and x1 of 0 in this stationary point process. And both of them, we know what happens to them. But turns out that, the joint distributions becomes independent. And that's where this difference of two gumballs shows up. So I'm not saying it too precisely, but roughly that's how it happens.
But what arguments allows you to prove weak but not strong?
So
because you make coupling.
Yeah, yeah, I kind of went over that quickly. So the thing is that we study these excursions, and excursions have two parts. One is the part that where from small distance you go to big distance, and the second part, from big distance you come back to small distance. And going from small distance to slightly big distance, that you can handle. But coming from big distance to small distance, you could have gone very, very far away. And you don't have a handle on that. You don't have a concrete handle on that. So you just end up throwing that part away and saying that on time averaged level, it's not important. But if you are really trying to prove strong domain of attraction, you have to deal with those things. And we don't know how to do that. So we can do with this time average thing, because those excursions are not too big, they're not too frequent, that kind of stuff. Yeah.